All right, we're going to continue with section 14.9 in this video, and we are going to do number 7 on page 984. So I intentionally left number 8 up here because I want to compare and contrast the two. So number 8 was the last example we did where we were parametrizing a cylinder, and now number 7, in exercises 5 through 10, find the parametrization of the surface sigma. Sigma is the portion of the plane x minus y plus z equals 3 that lies inside the cylinder. X squared plus z squared equals 4. So that's x squared plus z squared. We're inside the cylinder, so it's less than or equal to 4. So now when we look at this, we can solve this for x, we can solve it for y, we can solve it for z. So we would use our favorite parametrization on here. Notice up here on the cylinder, we couldn't solve that for y or z, so we couldn't use our favorite parameterization here. These are two very different surfaces, but their parameterizations are going to look somewhat similar, and I'm doing them side by side so that we avoid getting confused between parametrizing a cylinder and parametrizing a plane, but not the whole plane, just a part of the plane that's inside of a cylinder. So because we see that there's a restriction on x and z, that's a clue to us that in parametrizing this plane, we want x and z to be our parameters. So we're going to solve this for y instead of solving for, we might naturally say, okay, let's solve for z because that's what we normally have, z equals some function of x and y. But because these are putting restrictions, this is putting a restriction on x and z, we want to make those our parameters, and we're going to solve for y. So we're going to let x be equal to x, then y is going to be equal to x plus z minus 3. And then we're just going to let z be equal to z. All right, so we were able to use our favorite parameterization because we could solve this thing for y. But now we have to keep in mind that this is the first example we've encountered where there are actually some bounds on our parameters. Before, our parameters were able to just run free, but now our parameters, we have x squared plus y z squared has to be less than or equal to 4. Now, this is a parameterization and we have our parameters, but what we don't want is, we would like to know, say, some numerical values that x varies between and some numerical values that z varies between, versus having x squared plus z squared is less than or equal to 4. Now, this is in the plane y equals 0 in the xz plane. This would just be a circle. So we would look at it in terms of that. So now, here what we would do is we would say, well, if I want some values for x and z to vary between, I can't use x varies between -2 and 2 and z varies between -2 and 2, because that'll give us a square, not a circle. So circle, what we're accustomed to is using polar coordinates, and then we're going to do that here for this circle as well. And that's how the parameterizations are going to end up looking a little bit similar. So here now we're going to let x be equal to r cosine theta. And we're going to let y be equal to, not y, I don't know why I keep, well, I do know I keep doing y, but I mean z. Z be equal to r sine theta. Now, because this is, if we were to look at this in the xz plane, it's actually a disk. So the r actually varies from 0 all the way out to 2. When you are parameterizing a cylinder, when you're on a cylinder, the radius does not get to vary. The radius is stuck at whatever those values are. So notice when you're parameterizing a plane inside of a cylinder, we need this flat surface, so the radius should vary. When you're parameterizing a cylinder, you are staying on the edge of the cylinder the entire time, so your radius should not vary at all. So now down here, what we now have is, if we're going to let x be equal to r cosine theta and z be equal to r sine theta, we need to change everything here to be in terms of r and theta, and those are going to be our new parameters. And then we can use we can use our bounds for r, which would be from 0 to 2, and our bounds for theta, which would be from 0 to 2 pi, to give us bounds for our plane. So now we have our vector function. Instead of being a function of x and z, it's going to be a function of r and theta. X is r cosine theta. Y is x plus z minus 3, but that now is r cosine theta plus r sine theta minus 3. So r cosine theta plus r sine theta minus 3. And then z is r sine theta. All right, now with that, we need to make sure we put our restriction on r and theta to make sure we stay inside of this cylinder, because if we let r vary, then it's going to go well beyond 2 if we let r go on to any value. Now theta going from beyond 0 to 2 pi is fine. It's just going to spin around over and over and over again in the same circle, but we have to make sure that we don't go beyond the radius of 2. So here our r is going to vary from 0 to 2, and our theta is going to vary from 0 to 2 pi. So you may wonder, okay, if you had a problem like this, can you leave it like that? I wouldn't advise it, only because with these parametrizations, what we're going to end up doing is having to integrate or do something to try to find surface area, and you're not going to be able to do anything with that at all if you leave it that way. So if you run into a problem like this where you can't give explicit numerical bounds on your r and your theta, or whatever your parameters are, not r and theta necessarily, then you need to change things from this to something like this where you can give specific numbers. So to answer that question, yes, you would need to change from here to this. All right, so now let's look at another type, another way we can parametrize a surface. So another type of surface that is fairly easy to parametrize is a surface of revolution. For example, suppose the surface S is obtained by rotating the function f of x about the x-axis, where x is greater than or equal to a and less than or equal to b, and f of x is greater than or equal to 0, then S has parametrization x equals x x equals x, y equals f of x times cosine of theta, z equals f of x times sine of theta. And now our bounds and our parameters are x varies between a and b, and theta varies between 0 and 2 pi, where theta, so this is not our usual theta, that is the angle subtended from the positive x-axis. So this is where theta is the angle subtended from the positive y-axis. In a counterclockwise direction. In the xz plane. So a couple of things to point out. One, I said for example here because we could have that you were rotating around an axis other than the x-axis. So this is if you're rotating around the x-axis. This is what you get, x stays x, and then your radius basically is your f of x on your y and your z. If you were rotating around the y-axis, y would be equal to y, and then x would be equal to f of x cosine theta, and z would be f of x sine theta. Also, here I said that theta is going to vary between 0 and 2 pi. That's if you want to go all the way around the axis. You may not want to go all the way around the axis. So theta could vary between different values other than 0 and 2 pi. So that's why I said for example. So now let's look at an example using this parametrization. So we're going to do number 10. So in exercises 5 through 10, find a parametrization of the surface sigma. So in 10, sigma is the part of the paraboloid x equals y squared plus z squared for x less than or equal to 4. So x equals y squared plus z squared for x less than or equal to 4. All right, so if you saw this problem, what you should automatically do, because what you should do every time you ask for a parameterization is see, can I solve for x? Can I solve for y? Can I solve for z? And here the answer is yes. They've already solved for x for us. So the natural parameterization would be this. X equals x, y equals y, z equals z, x equals this. But then that tells us y squared plus z squared is equal to x. It says y squared plus z squared is less than or equal to 4. And then you would have to switch to y equals r cosine theta and z equals r sine theta to make sure that you're bound, that you actually could specify your bounds on your parameters. So that would be the natural parameterization. So try it that way as well. That's y equals y, z equals z, x equals y squared plus z squared, and then use polar coordinates to switch to r and theta for your parameters. we're going to do it using the rotation or surface of revolution, excuse me. So first, just to kind of get an idea of what's going on here, let's look at this in the XZ plane, or you can look at it in the XY plane. Either one is fine. I'm going to look at it in the XZ plane, or because the way I set up, I think I gave you all rotating around the x-axis. So it doesn't matter which way I look at it. Let's look at this in or actually, yeah, I gave you all. Let's look at it in the XY plane. Then it's our usual. We're accustomed to y being a function of x instead of z being a function of x. So we'll look at it this way. All right. So now what I want to do, and we are in the actual XY plane. What does this thing look like? So in the XY plane, this is where z equals 0. Now, what it looks like when z equals 0, it's going to look like we would get x equals y squared, which is a parabola that opens to the right, but we don't want to sketch the whole parabola. We're going to sketch that part of the parabola, and then we'll sketch the bottom part just as a dotted line. So we know that in actuality, that's what it would look like. But now, if we want to use a surface of revolution, we can look at, okay, in 3 dimensions, what we would get is this thing is going to look like this. Now, you don't have to go through all of this when you're doing a problem like this, but just so you kind of understand what's happening. So what did we just sketch? We just sketched that right there. So that's what we just sketched. So now let's just go ahead and do the other side of it and then put that on the front. And that's what this thing's actually going to look like. The surface is going to be this thing, and it's getting so that is this being spun around the x-axis. So that means we can use the parameterization x equals x. And what is our f of x here? Our f of x is, what is that function right there? So remember, this that we have right here is x equals y squared. So if we take x equals y squared, which is what we would get there, and we look at that's y equals plus or minus the square root of x. But our surface of revolution specified that f of x needs to be greater than or equal to 0. So we're just looking at that part, and that's just going to be the square root of x. So now what we can do is we can take the square root of x, spin it around the x-axis. It's going to give us this thing. Now, how do we parametrize that? That is x equals x, y equals f of x times cosine theta. Our f of x is square root of x times cosine of theta. And z equals f of x times, so square root of x times sine theta. And notice I said that theta is the angle subtended from the positive y-axis in, I hope I said the YZ plane. That's what I meant if I did not say the YZ plane. So let me check, make sure I did. Oh, I did not. I said the XZ plane. And that is incorrect. So let's go back and fix this. It is the YZ plane, not the XZ plane. Of course, we can't go around the y-axis in the YZ plane because the y-axis is not in the YZ plane. So fix that, please. That's the YZ plane. So now that's fixed. So theta is the angle subtended from the positive y-axis in the YZ plane. So theta, we're spinning around this way. And that's what we're doing because the z-axis would actually be coming out of the page at us here. And we would spin around in the YZ plane. We would come here and spin out of the page towards ourselves. And that will spin this thing around and spin there. So you're actually spinning the YZ plane, not the XZ plane. Sorry about that. All right, so now always check, do we need some bounds on our parameters? So here we were told that x has to be less than or equal to 4. So that's how this thing is getting cut off right there, or this would get cut off. So if you want to on this picture, you can sketch right there and say that's 4. So x then varies from 0 to 4. And theta, because we want to go all the way around, we want to get this full paraboloid, theta is going to vary from 0 to 2 pi. All right, so again, this wouldn't be the natural parameterization to use here. You would use your favorite parameterization. So try to parameterize it using your favorite parameterization. It will not look the same as this, and that's fine. So you can parameterize a surface in a number of different ways, just as you can parameterize a curve in a number of different ways, and you'll still get the exact same thing.